Nanomaterials are like the tiny building blocks of a Lego set, but much, much smaller. So small that you need a powerful microscope to see them. Imagine if you could shrink down to the size of a single grain of sand. These nanomaterials would still be thousands of times smaller. They are made up of particles or structures less than 100 nanometers in size, which is about 1,000 times thinner than a human hair. Because of their minuscule size, they have unique properties that aren't seen in larger materials, like being super strong, highly conductive, or having special magnetic qualities. For example, the carbon atoms in a pencil lead, graphite, can be rearranged into a different form called graphene, which is only one atom thick but stronger than steel and conducts electricity better than copper. These extraordinary properties make nanomaterials incredibly useful in creating everything from stronger, lighter materials for sports equipment to advanced medical treatments that can target diseases at the cellular level. Nanomaterials represent a revolution in the way we understand and manipulate matter. At the nanoscale, materials behave differently, exhibiting enhanced properties that defy our everyday experiences. Imagine a material stronger than steel, yet lighter than a feather. The potential applications of these properties are vast, spanning across various fields and industries. From improving the efficiency of solar cells to delivering drugs directly to cancer cells, nanomaterials are poised to revolutionize our world. To grasp the transformative power of nanomaterials, let's look at a familiar element: silver. Silver nanoparticles, measuring just billionths of a meter in size, exhibit remarkable antimicrobial properties. This remarkable property has led to the incorporation of silver nanoparticles in a wide range of applications. Imagine a world where hospitals are free from the constant threat of bacterial infections. The use of silver nanoparticles in consumer products is a testament to the growing impact of nanotechnology on our everyday lives.
The formal birth of nanotechnology is often attributed to physicist Richard Feynman and his visionary talk, "There's Plenty of Room at the Bottom," delivered in 1959. Feynman challenged the scientific community to explore the vast potential of manipulating matter at the atomic and molecular levels. The invention of the scanning tunneling microscope, STM, in 1981, and the atomic force microscope, AFM, in 1986, revolutionized our ability to see and manipulate individual atoms. These powerful tools opened a window into the nanocosm, allowing scientists to visualize and manipulate atoms with unprecedented precision. The 1980s also witnessed the discovery of fullerenes and carbon nanotubes, igniting a surge of interest in nanomaterials and their potential applications. With the ability to see and manipulate individual atoms, scientists began to explore new ways to synthesize nanomaterials. This era marked a shift from the top-down approach to the bottom-up approach, where nanomaterials are built atom by atom or molecule by molecule. Techniques like chemical vapor deposition, CVD, and sol gel processing emerged as powerful tools for building nanomaterials with atomic precision. Scientists developed new methods to probe the structure, composition, and properties of nanomaterials with increasing accuracy and precision. This rapid progress paved the way for the development of numerous applications, bringing the promise of nanotechnology closer to reality.
As we delve deeper into the world of nanomaterials, it's essential to understand that their properties and potential applications are intricately linked to their size and shape. In the realm of nanomaterials, size truly matters. Zero-dimensional, 0D, nanomaterials, like nanoparticles and quantum dots, exhibit unique properties due to their incredibly small size and high surface area. One-dimensional, 1D nanomaterials, like nanowires and nanotubes, offer exceptional strength, conductivity, and surface area. Two-dimensional, 2D nanomaterials, like graphene, possess remarkable electronic and mechanical properties, paving the way for flexible electronics and advanced sensors. Zero-dimensional nanomaterials, the smallest members of the nanomaterial family, are true giants in the world of technology. One of the most well-known examples of zero-dimensional nanomaterials is gold nanoparticles. This unique optical property makes gold nanoparticles invaluable in applications like biomedical imaging and cancer treatment. Beyond gold, other metals like silver, platinum, and palladium also exhibit unique properties at the nanoscale. Quantum dots, another fascinating class of zero-dimensional nanomaterials, emit light of specific wavelengths depending on their size, making them highly valuable in applications like displays and LEDs.
One-dimensional nanomaterials, with one dimension outside the nanoscale, resemble tiny wires, tubes, or rods, offering unique properties that make them ideal building blocks for various technological advancements. Imagine a wire 1,000 times thinner than a human hair, yet stronger than steel and capable of conducting electricity with incredible efficiency. This is the promise of carbon nanotubes, one of the most well-known examples of one-dimensional nanomaterials. Nanowires, another fascinating class of one-dimensional nanomaterials, are ultra-thin wires with diameters on the order of nanometers. In the field of electronics, nanowires hold the key to developing smaller, faster, and more powerful electronic devices. Two-dimensional nanomaterials have taken the scientific world by storm. These materials possess remarkable electronic, optical, mechanical, and thermal properties. Imagine a material as thin as a single atom, yet stronger than steel and more conductive than copper. Graphene, isolated in 2004, exhibits exceptional strength, conductivity, and flexibility. Beyond graphene, other two-dimensional materials have emerged, each with unique properties. The rise of two-dimensional materials has ushered in a new era of materials science, the strength of giants, mechanical properties at the nanoscale. Imagine a material as thin as paper, yet strong enough to stop a bullet. This is the remarkable reality of nanomaterials. At the nanoscale, materials exhibit extraordinary mechanical properties. These properties stem from unique atom arrangements and increased surface area. Carbon nanotubes are over 100 times stronger than steel. These cylindrical structures are ideal for reinforcing composite materials. Imagine airplanes and cars built with nanomaterial reinforced composites. The potential applications of nanomaterials are vast and continue to expand. Supercharged pathways, unlocking enhanced electrical properties. Nanomaterials are like supercharged pathways, facilitating electron flow with unprecedented efficiency. Graphene reigns supreme in electrical conductivity. Imagine electrons zipping through graphene like race cars on a superhighway. This makes graphene ideal for next-generation transistors, promising faster speeds and lower power consumption. Carbon nanotubes also exhibit remarkable electrical properties. Their tunable conductivity makes them versatile for various electronic applications. Metal nanoparticles, like gold and silver, exhibit unique electrical properties at the nanoscale. These properties make them suitable for conductive inks, sensors, and molecular electronics. As research progresses, expect more breakthroughs, leading to smaller, faster, and more powerful electronics. Tiny furnaces and efficient heat pipes. Thermal properties of nanomaterials. Nanomaterials excel in thermal conductivity and insulation, efficiently transferring or blocking heat. Graphene, with its unique atomic structure, enables efficient heat dissipation. Ideal for thermal management in electronics, graphene prevents overheating. Carbon nanotubes also exhibit exceptional thermal conductivity. Acting like tiny heat pipes, they channel heat away from components. These properties shape the future of electronics, energy, and medicine. A spectrum of brilliance. Exploring the optical properties of nanomaterials. When it comes to interacting with light, nanomaterials transform into a kaleidoscope of brilliance, exhibiting a spectrum of optical properties unseen in their bulk counterparts. These unique interactions with light arise from quantum mechanical effects, specifically quantum confinement, where the movement of electrons is restricted by the nanoscale dimensions of the material. This confinement leads to fascinating phenomena like size-dependent color, fluorescence, and enhanced absorption and scattering of light, opening up a world of possibilities in fields like displays, imaging, and sensing. Imagine a single material capable of emitting different colors simply by changing its size. This is the captivating world of quantum dots, semiconductor nanocrystals that exhibit size-dependent fluorescence. As the size of the quantum dot decreases, the energy levels within the material become quantized, meaning they can only take on specific discrete values. When a quantum dot absorbs light, it excites an electron to a higher energy level. As the electron relaxes back to its ground state, it emits light of a specific color that depends on the energy difference between the two levels. This tunable fluorescence makes quantum dots ideal for applications in displays, LEDs, and biological imaging, where they can tag specific molecules or cells with distinct colors. Metal nanoparticles, like gold and silver, also exhibit fascinating optical properties due to a phenomenon known as surface plasmon resonance. When light interacts with these nanoparticles, it excites the collective oscillations of electrons on their surface, known as surface plasmons. This resonance leads to enhanced absorption and scattering of light at specific wavelengths, depending on the size, shape, and composition of the nanoparticles. This property is responsible for the vibrant colors observed in stained glass windows, which have unknowingly utilized the optical properties of gold nanoparticles for centuries. The ability to manipulate the optical properties of materials at the nanoscale offers a powerful toolkit for developing innovative technologies in various fields. From high-definition displays and LEDs to ultra-sensitive sensors and advanced imaging techniques, the unique interactions of nanomaterials with light are illuminating the path towards a brighter future. Top-down approaches, sculpting materials at the nanoscale. Imagine a sculptor, chisel in hand, meticulously chipping away at a block of marble to reveal the intricate details of a hidden masterpiece. This, in essence, is the principle behind top-down approaches in nanomaterial synthesis. Lithography is widely used in the semiconductor industry to create intricate patterns on silicon wafers for microchips. Focused ion beam, FIB, milling is used to create nanoscale structures by sputtering away atoms. Bottom-up approaches. Assembling atom by atom. Imagine building a complex Lego structure brick by brick. This is the principle behind bottom-up approaches in nanomaterial synthesis. These techniques involve assembling nanomaterials from atomic or molecular building blocks. It's like having a molecular scale construction kit. One such technique is chemical vapor deposition, CVD. In CVD, a precursor gas is introduced into a reaction chamber. The gas molecules decompose on a heated substrate, depositing atoms or molecules. By controlling the reaction conditions, it's possible to grow high-quality films and nanostructures. Another approach is the sol-gel process. a wet chemical technique. Metal alkoxides are hydrolyzed in a solvent, forming a colloidal suspension. These particles condense, forming a three-dimensional network. The gel is dried and heat-treated, resulting in a porous solid. Self-assembly harnesses the tendency of molecules to organize into ordered structures. Molecules and nanoparticles can self-assemble into complex architectures. This approach creates intricate nanostructures with control over size, shape, and functionality. Bottom-up approaches create materials with atomic precision and control over properties. They face challenges in scaling up production for industrial applications. As research progresses, bottom-up approaches will shape the future of nanotechnology. Choosing the right tool for the job. Top-down and bottom-up approaches are complementary tools in nanomaterial synthesis, each with strengths and limitations. The choice depends on factors like size, shape, and cost-effectiveness. It's like choosing between a sculptor's chisel and a Lego set. Top-down approaches excel in microelectronics, but have limitations at the nanoscale. Bottom-up approaches offer versatility and atomic precision, but face challenges in uniformity. Often, a hybrid approach combining both methods is optimal. The future of nanomaterial synthesis promises new discoveries and unmasking the nanocosm. Microscopy techniques. Venturing into the nanocosm is like embarking on an expedition into an uncharted world. We need tools to peer into this minuscule world and reveal its hidden wonders. Enter microscopy techniques, the indispensable eyes of nanotechnology. These tools act as our windows into the nanocosm, unraveling the mysteries of matter. Atomic force microscopy, AFM, images surfaces with atomic resolution without damage. AFM uses a sharp tip to scan the surface of a material. Deflections are detected by a laser, constructing a topographic map with atomic resolution. Scanning electron microscopy, SEM, bombards the sample with electrons for a grander view. SEM visualizes the surface of nanomaterials with exquisite detail. Transmission electron microscopy, TM, uses electrons passing through an ultra-thin sample. Unveiling the molecular fingerprint spectroscopy in nanomaterial characterization. Spectroscopy techniques delve deeper, unveiling the molecular fingerprint of nanomaterials, revealing their unique chemical composition and electronic structure. These techniques exploit the interaction of light with matter, providing valuable insights into nanomaterials. Raman spectroscopy reveals the vibrational modes of molecules within a material. When light interacts with a molecule, some photons are scattered inelastically, losing or gaining energy. This energy shift corresponds to the vibrational frequencies, providing a unique molecular fingerprint. Raman spectroscopy is useful for characterizing carbon-based nanomaterials like graphene and carbon nanotubes. Section 3. Beyond the conventional. Exploring other characterization techniques. While microscopy and spectroscopy provide a wealth of information, the evolving landscape of nanotechnology demands diverse characterization methods. We need to explore techniques that probe unique characteristics and behavior. Dynamic light scattering, DLS, characterizes nanoparticles in solution. DLS exploits Brownian motion to determine size distribution. Zeta, potential analysis assesses surface charge, crucial for stability. Techniques like laser flash analysis, LFA, probe thermal properties. LFA uses a laser pulse to measure thermal diffusivity and conductivity. The world of nanomaterials Nanomedicine, a revolution in healthcare. Imagine a world where diseases are treated at the cellular level, with pinpoint accuracy. Nanomedicine leverages nanomaterials to revolutionize healthcare. From targeted drug delivery to advanced imaging, nanomaterials transform medicine. Targeted drug delivery is a promising application. Nanomaterials act as Trojan horses, delivering drugs directly to target cells. This minimizes side effects and improves treatment efficacy. Liposomes deliver chemotherapy drugs directly to cancer cells. Nanomaterials revolutionize medical imaging, offering more sensitive methods. Quantum dots provide brighter probes for optical imaging. They bind to specific cells, illuminating them under a microscope. This enables early disease detection and timely intervention. Nanomaterials are also advancing regenerative medicine. Nanofibrous scaffolds support tissue regeneration and repair. Nanoelectronics, powering the future of technology. Nanomaterials are revolutionizing electronics, enabling unprecedented miniaturization, speed, and energy efficiency. They offer a path to continue Moore's law, driving innovation. Nanomaterials are crucial in developing next-generation transistors. Graphene's electron mobility promises faster, energy-efficient transistors. Magnetic nanoparticles create high-density hard drives. Nanomaterials also enable flexible and transparent nanomaterials for a sustainable future. Nanomaterials offer innovative solutions for a more sustainable future. They play a crucial role in renewable energy, pollution remediation, and water purification. Enhancing solar cell efficiency is one promising application. Traditional silicon-based solar cells have limitations. Nanomaterials overcome these, enabling new solar technologies. Quantum dots absorb a wider range of light, converting more energy. They create multi-junction devices, maximizing energy conversion. Nanomaterials advance energy storage, addressing renewable energy intermittency. They improve battery capacity, charging speed, and stability. Nanomaterials also contribute to environmental remediation. They act as efficient adsorbents and catalysts, removing pollutants. Iron nanoparticles clean up contaminated groundwater. Nanomaterials in everyday life, from consumer products to industrial innovations. Nanomaterials enhance sunscreens, making them transparent and effective UV filters. They make clothes stain-resistant, wrinkle-free, and odor-resistant. In cars, nanomaterials improve performance and fuel efficiency. Buildings benefit from self-cleaning windows and better insulation. Nanomaterials are revolutionizing our world, enhancing product. Beyond the horizon, the next generation of nanomaterials. As we stand at the cusp of a nanotechnology revolution, it's exhilarating to envision the next generation of nanomaterials, poised to redefine the boundaries of materials science and unlock unprecedented technological advancements. Like explorers charting unknown territories, scientists are venturing beyond the familiar landscapes of graphene and carbon nanotubes, delving into the uncharted realms of two-dimensional materials, organic-inorganic hybrids, and bio-inspired nanostructures, each promising a treasure trove of novel properties and applications. The two-dimensional materials landscape, once dominated by the solitary brilliance of graphene, is now abuzz with a vibrant tapestry of atomically thin materials, each with its unique electronic, optical, and mechanical characteristics. Transition metal dichalcogenides, like molybdenum disulfide and tungsten diselenide, have emerged as frontrunners, captivating researchers with their tunable band gaps, strong light-matter interactions, and potential for applications in flexible electronics, optoelectronics, and catalysis. Imagine a world where electronic devices are as thin and flexible as a sheet of paper, seamlessly integrating into our clothing, accessories, and even our bodies. Beyond the realm of purely inorganic materials, the fusion of organic and inorganic components in hybrid nanomaterials is opening up new avenues for tailoring material properties with exquisite precision. Imagine combining the conductivity of a metal with the flexibility of a polymer or the biocompatibility of a protein. These hybrid materials, often synthesized using self-assembly techniques, leverage the strengths of their individual components while mitigating their weaknesses, creating synergistic combinations with properties unattainable in conventional materials. Taking inspiration from nature's ingenious designs, scientists are also exploring bio-inspired nanomaterials, mimicking the intricate structures and functionalities found in biological systems. Imagine nanomaterials that can repair themselves like living tissues, adapt to their environment like chameleons changing color, or harvest energy from their surroundings like plants through photosynthesis. These biomimetic materials, often synthesized using peptides, DNA, or viruses as building blocks, hold immense potential for applications in medicine, sensing, and energy. The Green Nanotechnology Revolution: Sustainable Synthesis for a Better Tomorrow. As the nanotechnology revolution gathers momentum, it's imperative that we consider its environmental impact and strive to develop sustainable practices that minimize its ecological footprint. This growing awareness has sparked a green nanotechnology revolution, a paradigm shift towards environmentally friendly synthesis methods that minimize waste, reduce energy consumption, and utilize renewable resources. Imagine a world where nanomaterials are synthesized using sunlight as energy, water as a solvent, and plants as raw materials, leaving behind a cleaner and healthier planet for future generations. One of the key principles of green nanotechnology is the use of benign solvents, replacing toxic organic solvents commonly used in traditional synthesis methods with environmentally friendly alternatives like water, supercritical fluids, and ionic liquids. These green solvents not only reduce the environmental burden associated with hazardous waste disposal, but also often lead to safer working conditions and milder reaction conditions, reducing energy consumption. Imagine a chemical synthesis lab that resembles a kitchen pantry, with shelves stocked with vinegar, baking soda, and plant extracts, replacing the harsh chemicals and noxious fumes typically associated with traditional labs. Another pillar of green nanotechnology is the development of energy-efficient synthesis methods, moving away from energy-intensive processes that rely on high temperatures, pressures, and long reaction times. Microwave-assisted synthesis, for example, has emerged as a promising alternative, utilizing microwave irradiation to heat reaction mixtures selectively and efficiently, significantly reducing reaction times and energy consumption. Imagine a microwave oven not just for reheating leftovers, but also for synthesizing nanomaterials with remarkable precision and speed. In the quest for sustainable nanotechnology, nature has become a wellspring of inspiration, with researchers turning to bio-based materials and bio-inspired synthesis methods to create eco-friendly nanomaterials. Imagine extracting cellulose from plants to create nanofibers for reinforcing composites, or utilizing bacteria to synthesize nanoparticles with intricate shapes and functionalities. These bio-based approaches not only reduce our reliance on fossil fuels, but also often lead to biodegradable and biocompatible nanomaterials, minimizing their environmental impact at the end of their life cycle. Convergence of Titans. Integrating nanomaterials with cutting-edge technologies. Nanomaterials are merging with AI and quantum computing, creating a technological singularity. This convergence promises intelligent devices, personalized medicine, and ultra-fast computing. AI algorithms predict nanomaterial properties, guiding scientists to promising candidates. In quantum computing, nanomaterials are crucial for developing next-gen computers. Quantum dots are explored as qubits, the fundamental units in quantum computers. Nanomaterials integrate with emerging technologies, creating hybrid systems with new capabilities. Navigating the nano-future, addressing ethical and societal implications. As we stand on the threshold of a nanotechnology revolution, it's crucial to acknowledge that with great power comes great responsibility. The same unique properties that make nanomaterials so promising also raise potential concerns regarding their impact on human health, the environment, and society as a whole. Navigating the nano-future responsibly requires a proactive approach, addressing these ethical and societal implications head-on, fostering open dialogue, and establishing robust regulatory frameworks that ensure the safe and equitable development of nanotechnology. One of the primary concerns surrounding nanomaterials is their potential toxicity. Their small size, while advantageous for many applications, also allows them to penetrate biological barriers and interact with cells and organs in unpredictable ways. While many nanomaterials are considered safe for their intended use, there is a need for comprehensive toxicity studies to assess their long-term effects on human health and the environment. Imagine a world where every new nanomaterial undergoes rigorous testing, similar to the clinical trials for new drugs, ensuring its safety before it reaches the market. Beyond toxicity, the ethical implications of nanotechnology extend to issues of privacy, equity, and access. Imagine a world where nanosensors embedded in everyday objects collect vast amounts of personal data, raising concerns about privacy and data security. Or envision a scenario where the benefits of nanotechnology, such as advanced medical treatments and enhanced consumer products, are only accessible to the wealthy, exacerbating existing social inequalities. Addressing these concerns requires proactive engagement with stakeholders, including scientists, policymakers, industry leaders, and the public, to establish ethical guidelines and regulatory frameworks that promote responsible innovation and equitable access to the benefits of nanotechnology. The nanotechnology revolution is not just about scientific breakthroughs and technological advancements. It's also about shaping a future that aligns with our values and aspirations. By fostering open dialogue, engaging in responsible research and development, and establishing robust regulatory frameworks, we can harness the transformation